All right, so we're on Unit 8. Now we're going to talk about hydrocarbons, but we're going to now involve oxygen and bring oxygen and their functional groups into our organic compounds. So we'll cover alcohols, we're going to cover ethers, aldehydes, and ketones, all different functional groups. Hopefully you guys have been trying to memorize all those functional groups. So we will cover 4 more today, and then the other 4 we're going to cover next week in Unit 9. So we've actually already been introduced into one functional group that contains oxygen. And those were done through an addition reaction that we looked at last week. So looking at those reactions, as long as we have an alkene, so here's an alkene, cyclopentene, plus we add some water to that, some acid, we'll use sulfuric acid. We're going to break that double bond. We break that double bond, and where we had that double bond at is where we're going to add our water. So we can either have it this way, or we can have it this way. And if you don't want to put the hydrogens in, it's not required to, because we're using the geometric formula. So we've actually already been introduced into this first functional group. So this first functional group here, this hydroxy, that is now bonded to our hydrocarbon, is what we're going to consider an alcohol functional group. So that changes the structure. So we have alkenes that we've talked. We have alkanes, alkenes, alkynes. We have alkyls. We had aromatics, and now our next functional group is what we're going to consider to be what we call alcohol. So alcohols are always going to contain this hydroxy group on there, bonded on one of the carbons in the main chain. So is this structure here, and because this structure has just one carbon, the derivative of this is what we're going to call methane. So here, because CH4 is methane, and if we draw CH4 out, an expanded structure, we have CH4, and this is what we consider methane. Well, now that we have an alcohol, we're gonna use pardon my dog here. Give me 1 second. Got 3 dogs. They're all fighting over this one crappy 99-cent bone that they all have to eat. Right? They can't even share it. One has, the other dogs have to bark at them to kind of like, hey, it's my turn. It's my turn. All right, back to our alcohol. So we're going to use this OL here. We're going to use that suffix when we change the name of our methane, because now our methane contains this substituted group here, this functional group, alcohol. So we're going to go from methane, we're going to remove this E, and we're then going to call it methanol with an OL. So we drop that E and we add in our OL. So methane, we're going to get methanol. Here's ethane. So there's 2 carbons, 6 hydrogens. We have ethane. And if I happen to remove one of those hydrogens and replace it with an alcohol functional group, then we're going to get I'm going to remove this E and I'm going to add OL. So we're going to get ethanol. So we have methanol, ethanol, propanol, butanol, pentanol, hexanol, and so on, right? So we have all of these new names that we have for our alcohols. One that we learned last week as well was this phenol, right? This phenol, phenol, potato. But we have this benzene ring here, and we call it phenol. And you'll notice the end of phenol does still have that OL, signifying that yes, we do have a functional group, that this is an alcohol, right? It's an alcohol, it's a benzene derivative here. So again, we're just going to simply remove that E from the name, and then we're going to add in OL. So we're going to have a bunch of different kinds of alcohol. So here, let me draw one. All right. So here's a 5-carbon structure, and just like our substituted groups, so we had our alkyls, we had our halogens, is that we want those substituted groups on the lowest numbered carbon we can put them on. Well, the functional groups, there's an hierarchy here, is that the functional group has a higher hierarchy, a higher priority in the numbering system than your halogens. Actually, you know what? Let me back that up a little bit. We'll say halogens. You know what? I think we'll just keep going with that. We didn't put in double bonds in there, but we probably should. So let's back that up. So our functional groups have a higher priority than our double and triple bonds, which have a higher priority than our halogens, which have a higher priority than our alkyl groups. Right? So there is an hierarchy here. So because we see a functional group here, is that that's going to have the highest priority in our numbering system. So we want that functional group on the lowest numbered carbon we can put it on. So if I number this, well, I'm going to number this from right to left. That way my alcohol group is on carbon number 2. And then if I draw this, I'm going to have to put him downstairs. I have this big 100-pound Great Dane here, crying over. You know what he is? I should, if I could show you this image, right? I have a little rat dog. I have a little rat dog that weighs about 5 pounds, and then I have a 100-pound Great Dane, and he's crying. That's my Great Dane crying over this bone from my little rat dog. Hold on, I'm going to put him downstairs. It's a little too much. All right, I'm back. Don't ever try and wrestle a 100-pound Great Dane. All right, so I'm going to actually move this functional group. And now I'm going to put it over here. Well, if we look at the structure on the left, it's 5 carbons long. 1, 2, 3, 4, 5. And the structure on the right, well, it doesn't really matter which way we count it. I'll just count it the opposite way this time. 1, 2, 3, 4, 5. It would still be carbon number 3, regardless if I number it from right to left, left to right. But now if we name these, well, they both come from pentane, but we drop that OH and we're going to write pentanol. And over here, 5 carbons, this is also pentanol. But this isn't unfamiliar territory that we're dealing with, is that they're both named pentanol, but similar to how we name our alkenes and our alkynes, wherever the double bond or the triple bond began, we gave it a number as to which carbon it began on. So here we're actually going to determine what number this alcohol functional group is on, and we're going to use that in the name. So this would actually be 2-pentanol, and this would be 3-pentanol, signifying where the location of that where the location of that alcohol functional group is at. So if we draw another structure, here the alcohol group happens to be on carbon number 2, so this is going to be 2. I'm going to drop the E from butane, and I'm going to write in this OL, so I have 2-butanol. We could put it on carbon number 1. Let's try that. So here it is on carbon number 1. 1, 2, 3, 4, and then this would be 1. Butane. I'm going to drop the E, and again I'm going to write in this OL, so I got 1-butanol. So we do have just a different variety, and also signifying. So here we see the 1-propanol, 2-propanol, 1-butanol, signifying to each one of these where that particular functional group is at. And then we're going to start naming structures such as this down here, right? Because we can have branches on there. As far as the numbering system goes, well, we're going to number it according to where the functional group is located. And then we're going to name it the same exact way how we named our branches last week in Unit 7. So here, let's draw a structure out. Here's my alcohol group. I'm going to put, let's put a methyl over here. Let's put, how about bromine over here? And I think that would be, yeah, let's name this now. Okay, so as far as numbering, the functional group here is closer to this side. So that's going to be my carbon number 1 here. So carbon number 1, 2, 3, 4, 5, 6. So here, my alcohol is on carbon number 3. And in 6 carbons, instead of saying hexane, I'm going to call it hexanol. I'll make sure that's an OL. On carbon number 2, I have a bromo. And on carbon number 4, I have methyl. Well, let's go alphabetical order here. So we're going to have 2, bromo, 4, methyl. And then I'm going to write this whole thing here, this 3 hexanol. And so here we'd have the name of that structure. Let's name it with, let's put a couple of the same branches. We've got some more branches in here. Let's draw another structure. All right, so now we've got quite a few branches in here. Let me throw in, no, I don't think I'll throw in another one. Nope, I think we're good with this. All right, so let's identify our branches here first. So here we have isopropyl, and we have a methyl group, we have another methyl group. Here we have an ethyl group. The hydroxy, or my alcohol, is closer to this end, so this is going to be carbon number 1, and I'll go ahead and number these. Carbon number 3, 4, 5, 6, 7. All right, so 7 would signify that this is going to be from hexane. So I have an alcohol group on carbon number 2, but instead of writing, heptane, not hexane. So here I'm going to drop that E, so this becomes 2-heptanol on carbon number 3, and on carbon number 3 again, so I'm going to have this methyl, and again I'm going to have methyl. On carbon number 4 I have isopropyl, and on carbon number 5 I have ethyl. Well, the two methyls, I'm going to put those together as 3,3-dimethyl. So I've kind of taken care of these two here. All right, now I'm going to go ahead and write the whole thing. I'm going to put it in alphabetical order. Ethyl's going to come first, so I'm going to have 5-ethyl. And then the isopropyl will come next, which is 4-isopropyl. And again, remember, we're not using di, we're using the methyl. We don't use Greek prefixes for, we don't use Greek prefixes as far as our alphabetical order. So I have 4-isopropyl. I'm going to have 3,3 because I have two methyls there. Di-methyl. And then I have room for my alcohol, which is going to be on carbon number 2. Heptanol. Make sure this is an O. So it's kind of a difficult structure there. And again, just a reminder, once they get this complex, is that I do just start listing everything that I have to make sure that I have everything. It's not uncommon. It's not wrong that if you want to circle all of the branches to make sure you have everything, circle the alcohol group, number them as I did to make sure that we get those names right. Here we have one that is in condensed structural formula. So here, because of the location of my alcohol group, so here's my alcohol group. Here's my branch. This is going to be carbon number 1, 2, 3, 4, 5, 6, 7. So again, we have heptanol. Well, it's on carbon number 2, and on carbon number 4, we have a branch, and it is ethyl. So 4-ethyl, 2-heptanol with an OL there. And now you're going to see a slight difference when we're talking about ring structures. So here, this would be cyclopentane. And then if we happen to put an alcohol on it, well, it's still the same process. Here, if we have hexane up here, we drop the E and we put heptane. We drop the E and we put heptanol. So we go from heptane to heptanol. Cyclopentane, we're simply going to drop the E again. I've dropped the E, and because of this alcohol here, I'm going to put OL. So this becomes cyclopentanol. There's my functional group. It's an alcohol. So instead of cyclohexane, I still keep the cyclo. Hexane, I drop the E, and I write in OL. So I have cyclohexanol. So I have cyclopropanol, cyclobutanol, cyclopentanol, cyclohexanol, cycloheptanol, and so on, covering all of our ring structures here. So the difference that we have here is that this is cyclohexanol. This is 2-hexanol. Now, if I were to draw it like this and put my alcohol group here, then this is 1-hexanol. And you'll notice here, it doesn't really matter if I change the location, is that in this structure here, this is carbon number 1 where the functional group is at. In this structure over here, this is carbon number 1 wherever the functional group is at. Right. So notice that I don't have 1-cyclohexanol. So in our ring structures, anything that we have, all these geometric formulas, all of these ring structures, is that I don't need to put in the location of that alcohol group. Only when I have an open structure, such as these down here, right? These line structures, these condensed form, is that when it's not closed up and it's not in a ring structure, I then have to put the location of where that alcohol functional group is at, right? But we don't necessarily need to do it with our ring structures. We can also have branches. We can't have branches on these ring structures. So here's an alcohol. Let's put chlorine over here, and maybe we'll put isopropyl over here. Right? So carbon number 1, wherever the functional group is at. Here is carbon number 1. And now I'm going to take the shortest path to the next functional group, carbon number 2. And then I'm going to continue numbering in this direction. So it's not always clockwise or counterclockwise. If I redraw this way, and I put my alcohol group here, chlorine here, and isopropyl down here, well, carbon number 1, I'm going to take the shortest path, and this is carbon number 2, 3, 4, 5. And it's the exact same structure that I drew next door. So on carbon number 2, chloro before isopropyl, so I have 2 chloro, 5 isopropyl. I don't have to put the location of the alcohol here because it's a ring structure. Cyclohexane, I drop the E, and I write NOL, so I got 5 chloro, 5 isopropyl cyclohexane. So now that's kind of combining everything that we know as far as naming our alcohols here. What we do have is that not all alcohols are the same. Is that we have different types of alcohols, right? Different classifications that we can classify them as primary alcohols, we classify them as secondary alcohols, tertiary alcohols. And it all depends on the carbon that's bonded to this functional group, this hydroxyl group. So I'm going to circle this over here. In each one of these cases here. So this is the carbon that's going to decide what type of alcohol that you have. Do you have a primary, secondary, or tertiary alcohol? Well, in order to determine that, we're going to count up the alkyl groups that are bonded to this particular carbon. The carbon that has the hydroxy group. The carbon that has the hydroxy group. And we're going to count up how many alkyls we have here. So in here, we have 1 alkyl. Primary alcohol. In the next one, there are 2 alkyl groups. Secondary alcohol. In the final one, right, we have 3 alkyl groups signifying that it's a tertiary alcohol. If we see this in line formula, let's see here. So here, this is what primary alcohol would look like. Secondary alcohol would look something like this. And a tertiary alcohol would look something like this. So here we're going to have 1 propanol. This is going to be 2 propanol. And this is going to be 2 methyl 2 propanol. But if I circle this here, there's my alcohol group. Here's the carbon. Here's my alcohol group. And here's the carbon that it's attached to. Here's my alcohol group. Here's the carbon that it's attached to. Here's my alcohol group. And here's the carbon that it's attached to. And in each case, I can identify how many carbons. So how many carbons are bonded to this carbon? Just this one. I know that there's 2 carbons on the chain, but I'm not asking how many are on the chain. I want to know how many carbons are directly bonded to this first carbon, to carbon number 1, where that alcohol group is at, and it is just 1 carbon. Primary alcohol. Here. 2 alkyl groups, secondary alcohol. 3 alkyl groups, tertiary alcohol. So when we're looking, let's look at the secondary alcohol again. Let me draw it longer here. All right, I'm going to circle it and identify this carbon here. Now, how many carbons are directly bonded to that carbon? Well, this carbon's bonded to it. This carbon's bonded to it. I don't want you to look at this carbon here. This carbon is not bonded to this carbon. This carbon's bonded to this carbon up here, right? So that's, we need to ask ourselves how many are directly bonded to this particular carbon here. So we have 1, 2, making this a secondary alcohol. So however many carbons are directly bonded to there signify. And we do need to understand why. We have to understand why, because when we undergo reactions, when we put these into reactions, is that each alcohol gives you a different product, right? Primary alcohols don't react the same way as secondary alcohols. They don't react the same as tertiary alcohols. Each one of these alcohols react differently, and if we can't identify what type of alcohol you have, well, then we don't know what the product of our reaction is going to be, because we're definitely going over a lot more reactions today than we did last week. Well, I don't know how many. It would probably be the same amount, but they're definitely more difficult, more complex reactions. All right, so we have a few down here that we can look at. And here, I found my alcohol group, and it's bonded to this particular carbon here. Now, how many carbons are bonded to this particular carbon? And it's just this one, making this a primary alcohol. Here, I'm circling it here. There's my alcohol group, and there's the carbon that it's bonded to. I have 1, 2, 3 carbons that are bonded to that, making that a tertiary alcohol. Here's my alcohol group here. There's the carbon that it's bonded to, and it's bonded to this carbon and this carbon, making it a secondary alcohol. And again, we just keep repeating this process. How many alcohol or how many carbons are bonded to this carbon? Well, there's this one here, and there's this one here. giving us another secondary alcohol. So however many alkyl groups that we have that are bonded to it is going to let us determine whether we have a primary, secondary, or a tertiary alcohol. So we can better understand what's going to happen once these undergo reactions. So alcohol, we've talked a little bit about solubility before. We've talked about solubility back in chapter 5 or chapter 6. And we know that water has these polar ends to it, right? We have a partially negative alcohol, partially positive hydrogen, and that this water molecule can make hydrogen bonds with another partially negative or partially positive hydrogen here. So here we have what we can form is this hydrogen bond. And remember again, these hydrogen bonds form between molecules. So this one's actually forming between methanol, and then I have water, I have another water molecule, I have another water molecule. And you can see that this one methanol is almost completely surrounded by water. Is that some alcohols can dissolve in water. Gas does not dissolve in water, right? If you've ever seen gas and water mixed before, the gas lays up top, the water lays on bottom, but it definitely doesn't mix, right? Definitely doesn't mix there. So again, some alcohols. Now, alcohols, we can determine which. It's not difficult to determine which alcohols will dissolve and which ones won't. It has to do with how large your alcohol is. So relatively small alcohols, methanol, ethanol, most of these can be surrounded by water molecules. So if I take this here, let me draw some water out. And now I'm going to make some hydrogen bonds. So this is going to bond here. We'll make hydrogen bonds. Oh, that's not. We'll make a hydrogen bond here. We'll make another hydrogen bond here. But we can see this small alcohol. You can physically see that I can get water around most of this small alcohol. Well, if I try to do the same thing with this larger alcohol, well, let's see the effect of this. So here, I'm going to put a water molecule. And I'll make some hydrogen bonds. And you can plainly see, I mean, look at all of this here. All of this does not get surrounded by water. We've talked about this particular bond before. Carbon-hydrogen bond is a non-polar bond. Similar to your diatomics. Your diatomics have non-polar bonds. Well, carbon-hydrogen is also one of your non-polar bonds. It means there's no polarity there, which means that water has no attraction. Water has no attraction to any of these carbons or any of these hydrogens, and it will not make a hydrogen bond. The only portion that's going to get a hydrogen bond is this alcohol group here. And that's the only part that we're going to be able to surround with water. So here, these larger chain alcohols can't be dissolved in water, right? Uh, if you know the name of gasoline, right, we call it octane, meaning there's going to be 8 carbons there. 8 carbons is a lot. So here's 1, 2, 3, 4, 5, 6, 7. So this is heptane. Heptane is insoluble in water. Well, if octane, which has 1 more carbon than heptane, is going to be a larger structure than this, then it's a safe assumption that it's also not going to be soluble in water. It's going to be insoluble. But small ones like ethanol, methanol, these small chain hydrocarbons here are alcohols here, are going to be able to be dissolved in water. So just kind of an understanding we have, and the reason for it, because the higher the mass, the less likely it is that it's going to be soluble. Propane, depending on the weather, if it's a really warm day or really warm where you're working, propane may dissolve in water. If it's a cold day, it may not dissolve in water. So I think propane, butane is kind of the breaking point there, where we're going to stop seeing these alcohols being soluble in water. All right. So the reaction the reaction from last week was hydration, right? We take some alkene. Here's my alkene, plus I'm going to add some water to it. We're going to need some acid. So again, we'll use some sulfuric acid. We break that double bond. We break the double bond, and we add our alcohol group to it, right? And this is what we consider a hydration reaction. Hydration. Well, what we didn't tell you is that this reaction is reversible. We can reverse the reaction. So if it's hydration to make our alcohol, well, we can also remove that alcohol and revert back to our alkene, and that's going to be labeled as a dehydration reaction because we're going to remove water from there. So for a dehydration reaction, the water is removed. It's just a reverse reaction of hydration. Hydration reaction, break the double bond, and add your reactant. Break the double bond, add the reactant. Dehydration is you're going to remove the water. So how we remove the water is very specific. So here, I'm going to insert hydrogens into here because they're not shown right now. So we are going to remove water, but we need to be careful as to how we remove the water. Is that we are going to remove a hydrogen, and we're going to remove the hydroxy group. And how we do it, well, here I see my hydroxy group. And now I have 2 hydrogens. I have a hydrogen over here, and I have a hydrogen over here. Well, we're only going to remove 1 group from each hydrogen. What? Good morning. Oh, I love you so much. Bye-bye. You gonna play with my Rubik's Cube? Okay. Don't lose it. All right, so here we need to make sure we're removing the correct hydrogen and the correct hydroxy group. All right, so if we remove this would not be good because now our carbon over here would only have 2 bonds. Love you too. So what we're going to do is, in order for this reaction to work, we're going to remove this hydrogen and this hydroxy group. So it's 1 on each carbon. We're going to move a group from this carbon. We're going to remove a group from this carbon. And this is where we're going to get our water from. So once we remove those, well, let me draw it here. I'll just kind of draw it up here. Once we remove those, this is the effect. This is, we'll just call this an intermediate. Right? So I've removed the hydroxy group, I've removed the hydrogen, and that formed our water. And now as we look at these carbons here, this carbon here only has 3 bonds, and this carbon here only has 3 bonds. So in order to fix that, well, that's where we're going to increase, and we're going to make a double bond here. Once we remove that water, we make the double bond. So a hydration reaction. Hydration reaction, break the double bond, and add our reactant where we broke it. Dehydration, remove the water, and where we remove the water, we're going to form, where we remove the water from, we're going to form a double bond between those 2 carbons. So always make sure that you're not removing the hydrogen and the hydroxy group from the same carbon, right? It's hydroxy group from 1 carbon, hydrogen from the carbon next door. So here, a dehydration reaction. We're going to remove this hydroxy group, and then we're either going to remove a hydrogen here, or we're going to remove a hydrogen over here. So in expanded structural formula, let me expand these hydrogens out just a bit. So here we have CH2, here's my COH. So either I'm going to remove these, or I'm going to remove these. Either way, we're going to end up with the same product. And we need some heat. So I'm going to use a little triangle for this reaction. We need some heat for this to take place. So what we get here, let me make an adjustment here. And we're going to remove these hydrogen, this hydrogen over here. There. So this is the hydrogen hydroxy group that we're going to get in order to get our water. And then because I remove them, I'm going to need a double bond between those 2 carbons. So let's number these carbons. Carbon number 1, 2, 3, 4, 5. So plus, I have CH3. I'm going to have a CH2. I have carbon here. There's my H. Carbon here. There's my H. And then I have CH3 because I removed that water. So I noticed that those 2 carbons there with the 1 hydrogen only have 3 bonds. So we're going to, where we remove that hydroxy group and the hydrogen to get our water, I need to form a double bond in between those 2 carbons. Oh, let's see, any other ones? This is the same reaction over here that we just did. It looks like they removed a different hydrogen. They removed the hydrogen here and 1 from over here. So that's why they're bonds. So what we have, and it's still the same. We have CH, what we had from up there. This is CH2, CH3. So this is what we have, right? Just to make sure, I don't want to confuse anybody here. We have CH3, CH2, CH, double bond, CH, CH3. Right? And that's what I have. So what I wrote here, all I did was take that and I rewrote it down here. Right? CH3, CH2, CH, CH, CH3. just so we can plainly see, if this is going to be carbon number 1, 2, 3, 4, 5, that this is still on carbon number 2, and this is also 2-pentene. Right? So 2-pentene, 2-pentene, they just removed the hydrogen on a different group, but we ended up with the same answer here. Let's look at something in line formula, I think. So I have some acid, H2SO4, some heat. Let's do so. Oh, all right. So here, let's make this into an alcohol. All right. So here's my alcohol. I'm going to add some acid to it. So this is a dehydration reaction. We're going to add some acid to it, add a little heat to it, and I have the option here. So I'm gonna draw in. We should understand that there's 2 hydrogens here, and that there are 2 hydrogens sitting here. Right? So I'm gonna use these here in order to make my water. So I've now made my water, and now where I remove that hydroxy and that hydrogen is where I'm going to put my double bond. Wherever we happen to remove that water from.
But it's okay if we went the other way, right? Like
it would be okay if you went the other way. Yep, absolutely. So you could have an answer that looks like this. That help?
Yeah.
All right. Let's look at one more. So here I have 2-pentanol. So 2-pentanol. We'll do the same reaction. We're going to use some acid. Plus, we're going to add some heat to that. We're going to remove that hydroxy group and make our water. And then we're going to put in our double bond. Or you could have this. Right. Either one is going to be acceptable. Because remember, we have 3 hydrogens on this end. We have 3 hydrogens on this end. So we're going to remove that hydroxy group, and then we're going to form our double bond. So that's what we consider a dehydration reaction. All right. So oxidation of, so these are now going to be some more complex reactions. Right? We've learned addition reactions. We have combustion reaction. We have halogenation of alkanes. And we now have dehydration reactions that we know. And now we're going to do something we're going to call an oxidation reaction. So because we're dealing with alcohols and we're dealing with these hydrogens, is that we're now going to consider what we call an oxidation of these alcohols. So we have to identify alcohols first. So primary alcohols. So here we have a primary alcohol. Let's figure out why it's a primary alcohol. Oh, I'm circling the wrong thing here. So here I have one alkyl group on it, making it a primary alcohol. So when it undergoes oxidation, that's how we have this here. That just means that I have some, remember those brackets? The brackets mean that that's a concentration, and the O is just an oxidizing agent, just a generic oxidizing catalyst. right? So when a primary alcohol undergoes oxidation, the result is that we're not going to remove the oxygen, this hydroxy here. Notice that there's a hydroxy on this particular carbon. And now if we look at this carbon, we have this oxygen that now has a double bond. So instead of removing this completely, we make a double bond to that oxygen, and we remove one hydrogen. So oxidizing a primary alcohol, we form a double bond to the oxygen, and we remove one hydrogen. Hydrogens are essential for oxidation. If there's no hydrogens, we can't oxidize. So primary alcohol, again, and I'll just keep repeating it over and over and over again because you do have to memorize these. So again, a primary alcohol, when a primary alcohol undergoes oxidation, we form a double bond to the oxygen from the carbon, and we remove a hydrogen. But we still have another hydrogen on this carbon. So it's not that I'm not looking at these hydrogens here. These hydrogens belong to this carbon. This carbon still has one remaining hydrogen, which means that it can undergo oxidation again. And this time, well, we're going to remove the hydrogen as well. We're going to remove this hydrogen, and in its place, we're going to put that hydroxy group back onto it. All right. So let's go over this one more time again, right? A primary alcohol, once it's oxidized, we form a double bond to the oxygen, and we remove a hydrogen. And then it undergoes oxidation again. We remove the hydrogen, and we add this hydroxy group. So the first time we oxidize, the very first time we oxidize it, we get something we call an aldehyde that we're going to go over in just a little while. And then the next time we oxidize it, we get something we call a carboxylic acid. Carboxylic acids we'll go over next week. Right? But we will definitely talk about aldehydes today, and this is just kind of an intro to carboxylic acids. We're not going to name these acids just yet. There's a lot of rules in naming carboxylic acids. So what we are going to learn today is we're definitely going to learn aldehydes. But again, this reaction is dealing with just primary alcohols. Secondary alcohols, we don't get the same result. Tertiary alcohols, we don't get the same result. Primary alcohols, and you just have to memorize this. Don't start questioning where these hydrogens are going. Where did the hydroxy group come from? Where's the hydrogen going? I don't understand. We just memorize it. Memorize, memorize, memorize. Primary alcohol. First time it's oxidized, we get an aldehyde. Second time it's oxidized, we get a carboxylic acid. And these are functional groups that you're going to have to memorize. Is that this is a functional group of an aldehyde. This, in its very subtle difference, is a functional group we call a carboxylic acid. If you guys go to 7-2 in your books, you'll see those functional groups listed. So we have to take time, we have to memorize all these functional groups and the way that they look. Now, this here, this is just a quick note, because in the lecture, this carbon that's double bonded to this oxygen. This is not a functional group. This is just a name that I'm going to be using. I'm going to be calling this a carbonyl. I'm not going to call it C double bond O. I'm not going to call it carbon double bond oxygen. I'm going to call it a carbonyl. So when I say the word carbonyl, you need to understand what I'm talking about. And I'm talking about a C double bond O. I'm talking about a carbon double bonded to an oxygen. But it's not a functional group. We're not going to name anything from a carbonyl. It's just the name of this particular structure. This is my carbonyl. So here, this aldehyde has a carbonyl and a hydrogen attached. A carboxylic acid has a carbonyl and a hydroxy group attached. Right? So this is what I'll refer to as a carbonyl. So again, this is just what happens to a primary alcohol. Primary alcohol, we oxidize it once, we get an aldehyde, which is a carbonyl and a hydrogen. Oxidize it again, we get a carboxylic acid, which is a carbonyl plus a hydroxy group attached. All right, let's look at secondary alcohols now. Actually, you know what? No, let's do a reaction first. Let's do a reaction going from a primary alcohol. So here's a primary alcohol. If I oxidize it, I'm going to use some oxidizing agent there. And if I oxidize it the first time, I'm going to get an aldehyde. So here, an aldehyde contains a carbonyl. There's my carbonyl, plus a hydrogen. And it still has the 4 carbons. Let's number this. So carbon number 1, 2, 3, 4. 1, 2, 3, 4. I want everybody to understand that this is not a carbon. That's not carbon number 1. Carbon number 1 is right here where we have this carbonyl. And that's carbon number 1. So the first time we oxidize a primary alcohol, we get a we get an aldehyde. The next time we oxidize it, we get a carboxylic acid. There's my 4 carbons, and a carboxylic acid, because we should be memorizing it, is a carbonyl plus a hydroxy group. And they're always done the same way. We're always going to get the same result from any primary alcohol. We oxidize it the first time. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. First time we oxidize it, we memorize it, that we get an aldehyde, which is a carbonyl plus a hydrogen. We oxidize it again, we're going to get a carboxylic acid. There's my 5 carbons, which is a carbonyl plus a hydroxy group. So primary alcohol, we're going to get an aldehyde. We oxidize it again. We get a carboxylic acid. So this is the result of working with primary alcohols. We get two different products from working with a primary alcohol. The first time we get an aldehyde, second time we get a carboxylic acid. Okay. Now with secondary alcohols. So instead of, and if we look at this one here, what we're going to get with secondary alcohols, let's not look at that reaction quite just yet. So let's draw a secondary alcohol. Yep. So here's a secondary alcohol. Secondary alcohol, when a secondary alcohol gets oxidized, well, this secondary alcohol only has this hydrogen here. So just as we saw in our primary alcohols here, primary alcohol, remove a hydrogen, form a double bond. We're going to remove this hydrogen, and we're going to form our carbonyl here, our double bonded oxygen. And this is what we call a ketone. And make sure that we right, it's not a ketone, right? It's a ketone, not a like a car key tone, right? But again, so here a much different result than a primary alcohol. And if we notice also, there's no more hydrogens on that particular carbon anymore. The carbon that had the alcohol group initially, there's no more hydrogens. So if we try and oxidize a primary or a secondary alcohol after it turns into a ketone, we're going to get no reaction from that. So we can't oxidize that again. So primary alcohol, we get an aldehyde, carboxylic acid. Secondary alcohol, we're only going to get a ketone, and we're not going to be able to oxidize it beyond that. So here, now we can look at this reaction here. So see where it says K2Cr2O7? This is an oxidizing agent. When we write this O with the brackets there, this is just some generic oxidizing agent catalyst, right? Nothing specific. So here we've actually noted something very specific, right? But again, it is an oxidizing reaction. We have a secondary alcohol. So here we have a secondary alcohol. These dashes and wedges, we didn't get a chance to talk about these dashes and wedges here. So I'm going to take a second and go over this. All right, so when you see these dashes and wedges, and I'm actually going to put CH3s on these here. So what these dashes and wedges mean is that if we see a darkened wedge here, like this one here, this signifies that whatever's at the end of that, so this particular CH3 here, that means that it is coming towards you. So we're trying to put some three-dimension perspective in a two-dimensional drawing. So this means that that particular group at carbon and three hydrogens is kind of pointing towards you. And this dashed wedge means that it's kind of pointing away from you. So here, if we're taking a look at this, well, that's kind of pointing away from it. So it's kind of behind the structure. The hydroxy group kind of coming towards us. So that's all those dashes and wedges mean. They're nothing special other than trying to give us some perspective, other than trying to give us some perspective on kind of the angles that we're looking at here. But they don't have anything to do with as far as the actual result here. So we're talking about secondary alcohol going into a ketone. So here we have this secondary alcohol. And I know it's secondary because here's the carbon we're looking at, and it's bonded to this carbon and this carbon, making it a secondary alcohol. And it does have an imaginary hydrogen. If we're looking at this particular carbon here, 1, 2, 3 bonds, and there's an imaginary hydrogen sitting there, giving us our 4th bond. So we remove this hydrogen and we form our carbonyl. Remove the hydrogen and form your carbonyl. So let's do another one here. Secondary alcohol. Let's use this one up here. So we've got K2Cr2O7. So we're going to remove the hydrogen and we're going to form a carbonyl there. So here, wherever that oxygen is at, I'm going to form a carbonyl, and this is my ketone. Let's see, how about we're going to take this secondary alcohol. It's going to undergo oxidation. Wherever that alcohol group is where we're going to form the carbonyl. Right? So every secondary alcohol will form into a ketone. Can it be oxidized again? Let's try and oxidize it. What happens? No reaction happens. Right? There's no more hydrogens there, no more hydrogens left in order to oxidize it again. All right. Tertiary alcohols. Well, tertiary alcohols cannot be oxidized. When we oxidize a primary alcohol, first time we oxidize it, aldehyde. Second time, carboxylic acid. But we can oxidize it because a primary alcohol can be oxidized twice because there's 2 hydrogens. A secondary alcohol can only be oxidized once because there's only 1 hydrogen. Well, there's no hydrogens on a tertiary alcohol, and you need to have a hydrogen on that particular carbon in order for it to oxidize. So if we have a tertiary alcohol and we try to oxidize it, we get no reaction from that. Right? Tertiary alcohols will not oxidize. So 3 different results as we're trying to understand these oxidation reactions. Primary alcohol, we get an aldehyde, which is a carbonyl plus hydrogen. Oxidize it again, we get a carboxylic acid, which is a carbonyl plus a hydroxy group. Secondary alcohol, we're going to form a carbonyl, and we're done. There's no reaction beyond that. So let's go over some more reactions here. So oxidation of 2-methyl, 1-propanol. So 2-methyl, let's see, propanol. So here's propanol, or propane. So there's propane, and carbon number 1 says I have an alcohol. So I have an alcohol on carbon number 1. So there's my 1-propanol. Carbon number 2, I have a methyl group. Well, this is a primary alcohol. Primary alcohol. If I oxidize it once, where that hydroxy group was at, I'm going to form a carbonyl, and I have an aldehyde. It doesn't really matter which direction that O is, carbonyl is pointed. It doesn't matter at this point. So we form an aldehyde first. If we oxidize it again, wherever that alcohol group was on carbon number 1, again I'm going to form my carbonyl, but this time I'm going to have a hydroxy group on it. So there's oxidation of 2-methyl-1-propanol. 3-pentanol. 1, 2, 3, 4, 5. And on carbon number 3, I'm putting my hydroxy group. So I've taken care of 3-pentanol. Carbon number 3, I have a methyl group. Well, this looks like a tertiary alcohol. We can't oxidize tertiary alcohols. So if I try and oxidize this, I'm going to get no reaction from a tertiary alcohol. Cyclobutanol. Actually, I think we already did cyclobutanol. So here's cyclobutane. If I put an alcohol on it, it's cyclobutanol. This is a secondary alcohol. So if we oxidize it, we're just going to form the carbonyl. Now we have a secondary alcohol, oxidizing to a ketone. All right. I think the last one, we've actually already talked about phenol before. I guess we can just kind of revisit this before, and then we'll probably just take a little break after we go ahead and name these here, because we're into a different functional group. So here we have to recognize, first off, that this is benzene. Actually, let me remove this. So this structure here is benzene. Right? But as soon as we put this alcohol group on it, we change the name of benzene to phenol. Right? So here, now this becomes phenol. And if we put branches on it, here we happen to have a methyl group on there, but it is phenol because I see this alcohol group on there. So this is phenol, and carbon number 1 is where we have the functional group. So this must be carbon number 2, and we have 2-methylphenol. Right? Carbon number 1, and it's not carbon number 1 because it's at the top. Right? That if I draw it this way, I do have students that think that this is carbon number 4 because it's not at the top. No, this is carbon number 1, wherever that functional group is at. So 1, 2, 3. So we have 3-ethyl phenol. We can draw some of these out. So as long as I know what phenol looks like, we memorize the structure. There's phenol. And it says we have 4-chloro, 3,5-dimethylphenol. So let's make this the alcohol group. So there's carbon number 1. I'm going to count in the clockwise position. So 1, this is carbon number 1, 2, 3 is a methyl, 4 is chloro, and 5 is my other methyl group. Let's put the hydroxy group in the bottom now. So here I have there. All right. So here, this is going to be carbon number 1. I have 2, 3, 5 triethyl. 2, 3, 5 triethyl phenol. Pentachlorophenol. Penta meaning 5. 1, 2, 3, 4, 5, and I'm going to surround it with chlorine. So here we have pentachlorophenol, 2,3,5 triethylphenol, and 4-chloro-3,5-dimethylphenol. So I think that covers everything we have to do with alcohols, plus a review on benzene rings and the derivative of that being phenol. All right, let's take a little break here. We'll take a little break. We'll come back at 9:30, and we're going to go and continue. And we're back. All right, so we've completely covered alcohols, I think. I don't think there's anything we missed. We covered our reactions, dehydration, oxidation, naming phenol. So now we'll talk about our ethers. So ether is another functional group. And ethers all have oxygen here. This is what we call an oxygen bridge. So all of our ethers have this oxygen, but you'll note it's not a carbonyl. Our carbonyl is an oxygen that's double bonded to a carbon, and all of these oxygens here have single bonds on them. Right? So these are going to be our ethers. There are different structures we can have for our ethers. So we take a look at this particular ether here. This is one way that we could write it. But we could also use line formula. Right? Whether you draw it like that or maybe you want to draw it like this. Nope. Right? Doesn't matter which way they point. They would both represent ether. So that's ether using line formula. Here, like this one down here, let's look at this one down here in particular. So this is what we call dipropyl ether. All this is signifying is that we have propyl, 1, 2, 3, 1, 2, 3. CH2, CH2, CH3, CH2, CH2, CH3. Because it's telling us this particular ether has two of those particular branches there. 3 branches instead of propane, it's propyl, right? But they're all alkyl branches bonded to these oxygens, right? This is methyl, not methane, it's methyl. This is ethyl. This is propyl. This is butyl. So we're going to use those alkyl names when we're naming our ethers. Right? So ethers are the simplest, probably one of the simplest compounds that we have to name here. So if I were to draw this, right, I'm going to circle the branches. So it's a little bit easier to identify. There's a lot going on in that last slide. So let's just kind of break it down to make sure we have this. So here I have my 2 branches, and these are 2 ethyl groups, and I want to make a note that this and this are not carbons. Here's carbon number 1, 2 for this branch. Here's carbon number 1 and carbon number 2 for this branch. Right? So I have 2 ethyls on here. And then we're going to use that Greek prefix. So I have di, ethyl, and then we put a space and we put ether. So diethyl ether. Ethers are very easy to recognize, right? I have an oxygen with 2 alkyls on ether side. Right? See what I did there? Even online, I can be funny, right? I have an oxygen with 2 ethers or 2 alkyls on ether side, right? That they're really easy to identify. So here, let's do another one. How about different groups, right? Here's an oxygen. I'm going to put a methyl on this side, and I'll put an ethyl on this side. And we don't name it right to left, left to right. We just name it alphabetically. Ethyl's going to come first, so we're going to write that branch, or we're going to write ethyl. And then I'm going to put a space in here. And I'm going to write methyl. And then I'm going to add another space. And I'm going to write ether. So we have ethyl, methyl, ether. And we'll notice that we have all those spaces between those, right? They're not meshed into one word, is that we have a space between all of those. So there's ethyl, methyl, ether. How about this one here? Let me redraw that one a little bit. It looks a little off. So I'll circle the branches here. Here's one branch. Here's another branch. This one is named butyl because there's 4 carbons. So instead of butane, butyl, right? Methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, so on and so on. This is isopropyl. So here, alphabetically, it is butyl space isopropyl space ether. We can even use geometric formulas. Geometric formulas also work. So here's my oxygen here. And let's put all right, so I have 2 geometric formulas here. So here, that is not cyclopropane. Nobody look at that and say that that's cyclopropane. Cyclopropane looks like this. It looks pretty similar, except we removed one of the hydrogens and we had to bond it to them. So just like we have methyl, ethyl, propyl, well, this is not cyclopropane, but this is cyclopropol. This is cyclobutol with a YL. So we put this together alphabetically, butyl before propyl, so we have cyclobutyl space. That's going to mess that up for me. Cyclobutyl, cyclopropyl, ether. Let's look at one more before we move on to those others. No, oh, actually, you know what? I think it's down here. We can use this one down here, right? So cyclobutyl ethyl ether, right? Well, as long as I know it's an ether, I'm just going to begin with that oxygen. Cyclobutyl on one side. So there's cyclobutyl, and ethyl on the other side. Another ether, so I start with my oxygen here. Cyclopropyl on one side, and then propyl 1, 2, 3 on the other side. So cyclopropyl, propyl ether. Then we have dicyclohexyl, which means that I have 2 cyclohexanes. Another way to write this, because I have 2 of them, right? If we take a look at this one up here, so let's take a look at this example. And notice because these 2 branches are exactly the same, look what they did here. They put it in parentheses, and then they just wrote the O. And even though it's a geometric formula, we can still do the same. And we can still write it this way, right? Signifying that there's two cyclohexyls on that particular oxygen. As far as reactions go, we're not going to go over any reactions regarding ethers. Regarding ethers, we're just going to identify them and name them. Or we can identify them and draw them like we just did. Right. So here, we drew it and then named it. And then down here, we had the name and then we drew it. So this is all that we're going to cover as far as ethers are concerned. All right, so now going back to aldehydes that we talked about earlier when we were oxidizing primary alcohol, right? Oxidize a primary alcohol, we get something we call an aldehyde. And I'm going to underline this AL. So with an alcohol, we went from methane, we drop the E, and we go methanol with an OL. Well, here, you'll notice this is an AL because it's an aldehyde. So instead of an OL, we're going to end them with AL. We still drop the E, but we're going to drop the E and we're going to write the letter A instead of the O, and we have methanol. So methanol, ethanol, propanol, butanol, right? And those are going to be all of our aldehydes. Right? Ethanol, like we see here, AL, AL, right? All of our ketones, we'll get into naming them in just a little bit. We're just going back because we're going to learn both ketones and aldehydes. So as far as ketones go, instead of an AL, we're going to end it with ONE. So instead of like propanol, right, here's ethanol, right? Instead of propanol, we'd have propanone, ONE, because it's a ketone, AL, because it's an aldehyde. So different naming conventions that we're going to have. So let's just first work with aldehydes. Right? For aldehydes, we never have to locate carbon number 1. Carbon number 1 is always going to be where the carbonyl is at for an aldehyde, not a ketone. Different rules for ketones, but as far as aldehydes go, wherever they see that carbonyl, that's going to be carbon number 1. So here we have 6 carbons. So instead of hexane, well, we drop the E and we replace it with Al. So we have hexanal. Right? There's my carbonyl. There's my hydrogen. Carbon number 1 is where the carbonyl is at. 2, 3, 4, 5. So instead of pentane, it is pentane. I drop the E and I replace it with Al, and I have pentanal. And naming our branches doesn't change at all. Naming the branches, we know how to name branches. We've been naming them for 2 weeks now, and nothing changes about naming the branches here. So here we see the one next door, 1, 2, 3, 4. Instead of butane, it's butanal. And then we name our branch, and that branch is at carbon number 3. We have 3-methylbutanol. So because aldehydes, that carbonyl, that functional group is always carbon number 1, we don't ever have to say 1-hexanal. This is not 1-hexanal. It's not necessary because for an aldehyde, it's always going to be carbon number 1, and it doesn't matter what the structure is. Actually, let me do this one here. This one. Right? Where's carbon number 1? Wherever this carbonyl is at. Carbon number 1. And we have heptane al. Carbon number 1, butane al. All right, and then we can start putting some branches. So let's go ahead and put in some branches now. Let's see. All right. So I know where carbon number 1 is, and I'm just going to go ahead and number this. So we know that it's hexanal on carbon number 2. There's a methyl. On carbon number 3, there's bromo. On carbon number 4, isopropyl. And I just kind of use my method that I always use, that I just kind of write everything down first, making sure I don't miss anything. Alphabetical order says I have 3 bromo, 4 isopropyl, 2 methyl, hexanal. Ones that aren't so complex but still have branches. Hydrogen here. Let's put 2 ethyls on. All right. Well, we know where carbon 1 is. That's wherever the carbonyl is at for an aldehyde. We know that this is an octane, so it's octanal on carbons number 4 and carbons number 5. I have 2 ethyls, so I'm going to put diethyl. So we have 4, 5, diethyl octanal. So our branches, and even as we continue on with ketones, carboxylic acids, esters, amides, and it doesn't matter, we already know how to name all of our branches. That was last week, and we should be good with naming all of our branches. For aldehydes, we may see this in an aldehyde. So here's my aldehyde, and I'm going to draw the same thing just down below here. All right, carbon number 1, carbon number 1. I'll just name them 3, 2, 4, 5, 6. So this is hex and al. Oh, misnumbered. If I did this, Well, instead of hexanal, well, carbons here, so instead of going from, we have to go from hexane, there's a double bond in here, so it's hexene. Then there's an aldehyde group on there, so this is now hexene al. Hexenal. And that double bond began on carbon number 3, so this is actually 3-hexene al. Right, there's our double bond there. Double bond begins on carbon number 2, so this would be 2. There's 3, there's 4 carbons here. So instead of butane, it becomes butene, butene, but there's an aldehyde, so I'm going to put Al for butanal. I'm not going to get too complicated or too crazy with these, but we can. Let's put a branch in here, and let's make a double bond in there as well. So this is about as complex as it's going to get, having these both in here. So let me number them. 1, 2, 3, 4, 5. So here I have a branch at carbon number 4. I have a double bond that begins on carbon number 2. So instead of pentane, it's pentene. That begins on carbon number 2. It's an aldehyde, so it's 2-pentene al. And carbon number 4 has a methyl. So this is 4-methyl 2-pentene, and it's an aldehyde, so 2-pentene al for the aldehyde. And that's about as complex as we're going to get for aldehydes. So then that brings us to, now this is just what we went over right now. That brings us over to ketones. Right. So ketones, well, we do have to identify where the ketone is at. Right? Just like we identified where the alcohol group was at, we identify where the ketone is at. So here in this particular example here, right, we notice that here it's on carbon number 3. And instead of saying, there are 6 carbons there, so instead of saying hexane, we drop the E, and it's hexane from our ketone. So let's look at some other examples here. We won't worry about the ones on the sides there. All right, 4 carbons, 1, 2, 3, 4. So instead of saying butane, right, we're going to drop the E and we're going to add ONE, and it becomes butanone, right, 2-butanone. Now, we don't want to cut too much off here because some students will do this, and they call it butone, right? And that's cutting off a little bit too much. Is the only thing we're dropping is we're just dropping the E, not the ANE. We're just dropping the E, so this becomes butanone, not just butone. We could just keep continuing on. I mean, it really wouldn't matter. So here we have 1, 2, 3, 4, 5 carbons. 5 carbons, and our ketones on carbon number 3. So 3 pentan. What do? We drop E, and we're going to write in ON. E, and we get 3 pentan O. And then we can have branches as well. So we notice on the one below here we have a branch. Here's my carbonyl. Let's go ahead and number this. 1, 2, 3, 4, 5, 6, 7, and 8. Right. So just to make sure there's no confusion, because I know that we go over this, and sometimes I don't know how it happens, but students assume from what we have from aldehydes, they say this is carbon number 1, and they go that this is an ethyl group, and that's not kind of what we're doing. What we're doing here is that there's just a little bit of confusion that lies there. So we're numbering this 1, 2, 3, 4, 5, 6, 7, 8. On carbon number 6, we have bromo. On carbon number 3 is where we have that carbonyl. So instead of octane, we're going to go octane. We drop the E. We were drawing right in ONE. So we write this as 6 bromo 3 octane O. And that's our structure there. Here, this is not in your book, but I did write it down that you did have to memorize this structure. Is that this structure here, whether we see it like this or whether we see it like this, and this comes from the last unit that we talked about, is that we recognize this as an aldehyde. So this is Benz aldehyde. So this is benzaldehyde. We talked about NO2, which is nitro. This is our halogen, which is chloro. Carbon number 1 is where the functional group is at. Let's see, chloro comes first before nitro. So we have 3 chloro, 4 nitro, and then we memorize the name benzaldehyde.
I think that should be a 5 nitro.
5 nitro, 1, 2, 3, 4, 5 nitro. Yep, you're correct. 5 nitro benzaldehyde. So benzaldehyde is a structure that you do need to memorize. Right? One of those structures that you do need to memorize. We're not going to have any double bonds on here. And then before we move on, actually, you know what? I think we could probably, let's name these because we do have to go over a couple of common names to these. So as far as ketones go, this is what we're going to consider. Let's go, let me redraw it here. So this is I'm not going to make it huge. I'll make it 2 pentan. 2 pentanone here. And this is the IUPAC system, right? So IUPAC, you don't have to memorize IUPAC. We didn't go over what it stood for. It's an International Union of Physical and Applied Chemistry. Like it's just, they're the ones that kind of designate how we're going to officially name these compounds. So the official IUPAC name of this structure is 2 pentanone. Well, there's also a common way to name this, that it does have a common name. And if I redraw the structure, and let's revisit our ethers. So if I drew this, could we name this particular ether? All right, well, it's an ether. I'm going to circle my branches. This is methyl. This is propyl. So I'm going to write methyl, I'm going to put a space, and I'm going to write propyl, and put a space, and then I'm going to write ether. Well, there's a common way to name ketones, and we use kind of this very similar concept as to how we name our ethers. If I circle this, and I circle this, and I think of this portion being itself, well, here's my ether. Here's my ketone. I have propyl here. I have methyl here, and I could name this methyl propyl ketone. And this is a common way that ketones are named. So we have an IUPAC name, which is 2-pentanone, and a common name of methylpropyl ketone. Let's get a couple more of those in here. Let's see. All right. So here is one branch. Here's another branch. This is butyl, 4 carbons. This is isopropyl. So we can name this butyl isopropyl ether. No, ether. No, butyl isopropyl ketone. Let's do one more here. Right. Here's a branch. We'll say this is another branch. So I have diethyl, and it's a ketone functional group. So diethyl ketone. So those are common ways to name these structures. Let's go ahead and name some of these here. So here, pentanone. And that's, you know what, something we didn't cover for ketones. We'll cover it now. This is pentanone, but it's also cyclo, which means as soon as I know cyclo, I already know to draw a geometric formula. And it's pentanone, which means 5 carbons. So here's 1, 2, 3, 4. So I do have 5 carbons in my geometric formula. And it does have a ketone. And there's my ketone structure. So wherever in a ring structure, right, we already know this is carbon number 1 in my ring structure where that functional group is at. And on carbon number 2, I have my 2,2-dimethyl. Right? So if I draw another structure here, right, could we name this structure? Yes, we could. This is cyclohexane. Right? Cyclopropanone, cyclobutanone, cyclohexanone, cycloheptanone, so on and so on. Here we have heptanal. So the first thing I'm going to do is I'm just going to simply draw heptane. I'm not even going to draw heptane out. I need heptane. I can turn heptane into whatever I need. I can turn it into an alcohol. I can turn heptane into an aldehyde, a carboxylic acid, a ketone. I could do whatever I need to heptane. So that's where my initial starting point is going to be. 1, 2, 3, 4, 5, 6, 7, and I've drawn heptane. Well, now I need to turn it into an aldehyde, and because I've memorized it, I know that an aldehyde is a carbonyl, and it's got a hydrogen on there for an aldehyde. I know that this is going to be carbon number 1, and 2,4,6-trimethyl. Carbon number 2, 4, 6 all have methyl groups. Here is bromopropanol. All right, so bromopropanol. Let me draw propane first. So I've drawn propane. And now, because of the ONE, I know it's a ketone, and the ketone is just simply a carbonyl. So here is my carbonyl. And let me see, we have bromopropanone. So let me put a bromine on this propanone. Okay. This one's kind of odd here. Just so I don't want there to be too much confusion, because normally when we name structure, so if I did this, I'd have to name this 2. I'd have to name it 2-pentanone. So this is 2-pentanone. But this over here, propanone, well, there's nowhere else to put that. There's nowhere else to put that carbonyl. If I decide to put the carbonyl somewhere else, well, let's put it on carbon number 1 and let's see what happens. I'm going to put a carbonyl here, and that means I have to erase a hydrogen. And, well, does that make a ketone? No, it certainly doesn't. It makes it propanal. It makes it an aldehyde. So the only place that I can put a carbonyl on propane is in the middle carbon. There's nowhere else it's going to go. So for propanone, that's the reason why it's not numbered 2-propanone. It's not number 2-propanone because I just simply can't put it anywhere else. The only place I can put it is on carbon number 2, which means that it's pretty obvious. I can't put bromine there. I can't do this because that puts 5 bonds around carbon. This carbon here has 1, 2, 3, 4, 5 bonds, so I obviously can't put it there. So what we end up doing is we don't end up using any numbers on this, is that there's nowhere else for me to put the carbonyl, and there's nowhere else for me to put the bromine. So this is just bromopropanone. Let's look at here. So I have 2-butanol. So let's draw butane first. So there's butane. Carbon number 2, I'm turning it into butane to butanone. And then 1,1-dichloro. Carbon number 1, I'm going to put 2 chlorines there. And I have, right, 1, 2, 3, 4. So 1,1-dichlorobutanol. Benzaldehyde. We're going to skip E for a second. So here's benzaldehyde, or benzene. In order for me to get benzaldehyde, I have to put an aldehyde functional group on it. This is going to be carbon number 1. On carbon number 2, I have methyl. And on carbon number 4, I have another methyl. So this is 2,4-dimethyl benzaldehyde. Then we get to dichloroacetaldehyde. So there are some other common names that we need to know. So these two prefixes here, acete and form. The prefix form is used for one carbon molecules. Acete is used for two carbon molecules. So we're going to name this first. So this is something that we've already seen previously. We've already seen this. This is an aldehyde. And I know it's an aldehyde because I see my carbonyl with a hydrogen signifying aldehyde. There's one carbon here, so as far as IUPAC goes, this is named methane. We drop the E, and we name it methanal. If I draw another structure next door, right? Again, I notice aldehyde functional group, but if we name the IUPAC, how we normally name these, because carbon number 1, carbon number 2, it's not ethane, but it's ethanal, methanal. But commonly, these are where we're going to use these prefix acete and form. When we use these common structures, right? How did we name this? We named it diethyl ketone, butyl isopropyl ketone. When we're using this common prefix, well, we're going to use aldehyde for the ending. So if this prefix form is used for one carbon molecules, then this is form aldehyde, formaldehyde, right? And this is common, right? IUPAC, methanal, commonly known formaldehyde. IUPAC, ethanal, commonly known as acetaldehyde. So formaldehyde, acetaldehyde, right? Acetone, right? Acetone, acetone, acetone. ONE because it's a ketone, and acete because there's two carbons, right? So acetaldehyde, formaldehyde. So there are some common ways that we're going to use these. Alcohols, let's go back and review alcohols because there's a common way to name alcohols similar to the common way we name ketones and how we name alcohols. I'm sorry, not alcohols, but ethers, right? Let me get to a blank page here. Do I have any blank pages? Yes, right? So here, right? This is methanol. This is ethanol. This is one propan all. Well, I don't know if you may have noticed this, but this looks like methyl, right? And this functional group is alcohol. So we could call this methyl alcohol, ethyl alcohol, propyl alcohol, right? This is commonly known, and this is IUPAC, right? So IUPAC, methanol, commonly known as methyl alcohol. IUPAC, ethanol, commonly known as ethyl alcohol, right? Um, you, I know somebody has this under their kitchen sink in the bathroom, right? This is, well, look at this here. Instead of labeling it as 2-propanol, it's commonly known as isopropyl alcohol, right? So common ways to name some of these groups, and then our IUPAC way that we know how to name those there. And I think that we're just about done. I think we have a couple more reactions to go over. Aldehydes. We're not going to name those.
So are we going over E or are we just...
Oh, that's right. We do have E to go over. So dichloro acetaldehyde, right? So E, thank you for that. So acete means that we have a 2-carbon molecule. A 2-carbon molecule that has an aldehyde functional group. So let's draw a 2-carbon molecule that has an aldehyde functional group. And then here it says dichloro, which means I have 2 chlorines. So dichloro. So this is dichloroacetaldehyde. We could draw it in line structure like this. And it would represent the same thing. So there's our dichloroacetaldehyde. And again, we know acete means 2 carbons. And then the aldehyde functional group is just one of these functional groups that you do have to memorize there. So dichloroacetaldehyde. Oh, and that brings us to these last 2 reactions here. So we have 2 reactions, or 2 reagents that we're going to talk about. We're going to talk about what we call Tollens reagent and Benedict's reagent. So Tollens reagent is a oxidizing reagent, right? So we know oxidizing reagents. We talked about oxidizing reagents before. So here's an oxidizing reagent, right? This is, other than putting this, like that, we have these oxidizing reagents. So this is what we consider a mild oxidizing reagent. So what happens here is that if we're not careful, or if we have too strong an oxidizing agent, is that we can take a primary alcohol. Primary alcohol, the first time we oxidize it, we get aldehyde. Second time we oxidize it, we get carboxylic acid. And it's completely plausible, if we're not either cautious or if we have too strong of an oxidizing agent, to blow right past this and get nothing but carboxylic acid. Right? So that is completely possible. So Tollens reagent is a mild oxidizing reagent. And what it tests for, it will test for uh, aldehydes to make sure that we didn't over oxidize and make a bunch of carboxylic acid. So Tollens reagent only works with aldehydes, and in order to, let me put some actual uh, compounds in here. And I think we might even have one. So here's Tollens reagent up here. So Tollens reagent is a silver and ammonia compound that we make, and it's a very clear solution. So this is Tollens reagent, right? Once we put an aldehyde, once we put any kind of aldehyde in that reagent, well, what happens is the silver comes out as a solid, right? And that's what we see in this test tube over here, is we see that solid's been released, silver, and this would signify that we tested positive, for an aldehyde. This doesn't work with ketones. We don't put ketones into Tollens reagent and have it oxidize, and then we get aldehydes from that. Is that this only works when we're testing aldehyde. So if we have a particular aldehyde, and we add in some Tollens reagent, is that our result is what we're going to consider a carboxylic ion. This is a carboxylic acid. Carboxylic acid, right? This is a carboxylic anion because we don't have the hydrogen there. If anybody's, don't worry about what this R is. This R is just any random alkyl. Could be methyl, ethyl, propyl, butyl. It could be anything, right? It's just some random alkyl group and nothing specific here. But we want to notice here, so what we get here is a carboxylic anion. So let's draw this carboxylic anion, right? It doesn't turn into a carboxylic acid, right? When we oxidize an aldehyde, we get a carboxylic acid. When we use this mild oxidizing agent, Tollens reagent, we're testing for aldehydes, and what we get is a carboxylic anion, plus we're going to get some silver as a solid. And let's see here. If I were to do this, this we test with aldehydes. And notice this is a ketone. Well, if we happen to try and test this with a ketone, we get no reaction from that. Right? There's no hydrogen to oxidize. We're using Tollens reagent, so we get this release of silver when we're testing aldehydes. Right? We're testing these aldehydes. Bendix reagents is something very similar, except we're going to be using some copper, and then we're going to get copper as a solid. But a very similar reaction. So this Bendix reagent is in this blue solution here, and what happens is if we put an aldehyde into that blue solution, well, we get copper as a solid in that reaction. And again, this only works with aldehyde. So let's get our aldehyde again. So there's butanal, plus we're going to get our Benedict's reagent here, plus some base, and we get again this carboxylic anion. Carboxylic anion. Here's my aldehyde. I don't lose any carbons. The only thing that happens here, so I get a carboxylic anion instead of a carboxylic acid. Plus, I'm going to get some copper as a solid, and then we'll get some water molecules over. And then if we happen to test it with a ketone, is again we're going to see that no reaction happening. Use these as templates. You have some homework done this weekend, or this week, and we're going over Tollens Reagent. Is the very last homework problem that you guys have, and use this kind of as a template to answer both of those questions there regarding writing some reactions. To be asked to write reactions, and we just did a couple of these reactions on each one of these. So what happens when we use a ketone, and what happens when we use an actual aldehyde, right? What happens when we use a ketone, and what happens when we use an actual aldehyde for these reactions. All right, and that covers Unit 8, went over our common terms, aldehydes. Yeah, next week we'll talk about esters, carboxylic acids, amides, and anions next week. So that'll cover, I think we're done with our lecture for today.